Okay, so we have a mechanics of materials practice final exam. Let's begin. Number one, uh, a stepped aluminum rod is rigidly fixed between two immovable walls at temperature 20 degrees Celsius. The rod consists of two segments. Segment AB, length 0.60 meters, diameter 30 millimeters. Segment BC, length 0.40 meters, diameter 20 millimeters. Temperatures increase uniformly to 95 degrees Celsius. Material properties, E equals 70 GPa, alpha 23 times 10 to the negative 6. Determine these three components: thermal stress in each segment, the axial force in the rod, and the total strain energy stored in the system. And I'm just going to go over this very quickly so it's an overview and you have this as a reference for extra practice problems. There are some intermediate steps that aren't shown, but if you feel like it, you could work out the problems for yourself just for extra practice. Okay, so this is an axial loading and thermal stress problem. Again, I'm going to go over these rather quickly because you could always pause the video and you have this as a reference. Compatibility. Okay, you have the change sub delta sub MECH plus delta sub thermal equals 0. And this P times the quantity L sub 1 over A sub 1 E plus L sub 2 over A sub 2 E equals alpha delta T times the quantity, the sum of L1 plus L2. And solving for P, we're going to get approximately 56.9 Kn. Okay, so since expansion is restrained, the force is compressive, and if we do the computation, we're going to wind up with sigma sub AB. That's going to be negative 80.5 MPa. Sigma sub BC, that's going to be about negative 181.1 MPa. And our P, as we said before, is 56.9 Kn compression. And last component here, the strain energy, we're going to use this formula, U equals P squared over 2E times the quantity L sub 1 over A sub 1 plus L sub 2 over A sub 2. Substituting those values that were given and we found, U is approximately 49.1 J. Okay, so that takes care of number one, and let's move on to number two. Okay, so number two, let's see what we have here. A steel bar of length 3L is fixed at both ends. Okay, concentrated axial load P is applied at a point located L from the left support. The cross-sectional area is constant throughout. Determine A, the reactions at the supports, the B, the normal stress in each region, and the displacement of the point of application of the load. Express answers in terms of P, L, A, and E. Okay, so this is a statically indeterminate bar problem. We're going to treat the two fixed portions as axial springs. So we're going to have the left stiffness as K sub L equals AE over L. Right stiffness, K sub R equals AE over 2L. And the displacement at the load point, that's going to be a delta. Pardon me for my horribly drawn deltas. Delta equals P over K sub L plus KR. All right, and here we have, here we're going to have this delta equals P over AE over L plus AE over 2L. Okay, and delta is going to be 2PL over 3AE. That's when we just simplify. I skipped over some steps algebraically, computationally. So our reactions, R sub L 2P over 3, R sub R P over 3. Okay, so from here, stress in the left-hand region, that's going to be sigma sub L is 2P over 3A. Stress in the right region, sigma sub R is negative P over 3A. And we could say here, the right side is compressive, okay, if the load pushes toward the right support. Okay, so that takes care of number two. Moving along, number three. Okay, at a point in a machine component, the plane stress state is Sigma sub x is 120 MPa. Sigma sub y is negative 40 MPa. And tau sub xy is 55 MPa. Part A, B, and C, let's see here. We want to determine the principal stresses, the maximum in-plane shear stress, the orientation of the principal planes, and the normal and shear stress acting on a plane rotated 25 degrees counterclockwise from the x-plane. Okay, so here's what we could do. This is a stress transformation in Mohr circle problem. We take what we're given. Average stress is going to be that sigma sub AVG equals 120 minus 40 over 2. You get 40 MPa. Then we're going to use the radius formula, R equals square root. Substitute the quantities we need. We have that 120 minus that negative 40 over 2. We're going to square it. And then we're going to add 55, that tau sub xy, 55 squared to it. So that's just the radius of about 97.08 MPa. And our principal stresses, doing the math, we're going to wind up with here, sigma sub 1 is about 137.1 MPa, sigma sub 2 is negative 57.1 MPa. Okay, and that's just that R added to the average stress, and then the average stress here minus the R to get the negative. Okay, you're probably very familiar with that. Maximum in-plane shear, well, that tau sub max is 97.1 MPa. And for the principal angle, we're going to set it up as tangent of 2 theta sub p equals 2 tau sub xy over sigma x sub x minus sigma sub y. And when we solve for that, we're going to get theta sub p is approximately 17.3 degrees. Okay, now from here at 25 degrees, we could say that this sigma sub x prime is about 133.6 MPa, and t sub x prime y prime, that's about negative 25.9 MPa. Okay, and that's after doing the computation. And now we can move on to number 4. Number 4 here. Okay, so for number 4, thin-walled cylindrical pressure vessel has internal diameter of 1.2, thickness 8 mm, and internal pressure 2.5 MPa. The material properties are E equals 200 GPa and nu equals 0.30. Determine A, the hoop stress, B, the longitudinal stress, C, the change in diameter, and D, the volumetric strain of the vessel. Okay, so this is a thin-walled pressure vessel problem. So to get the hoop stress, we take this, sigma sub h equals PR over T, and substituting their values, we get sigma sub h is 187.5 MPa. Longitudinal stress, sigma sub L, that's PR over 2T. Substituting our values, computing, we get sigma sub L is 93.75 MPa. Okay, to get the change in diameter, well, we need the circumferential strain first. Epsilon sub h is the sigma sub h minus nu sigma sub L divided by the E. Epsilon sub h, that's going to come out to, when we substitute our values and compute, 7.97 times, about 7.97 times 10 to the negative 4th. So our alteration in diameter is going to be delta D equals epsilon sub h times delta D. Substituting our values, the change in diameter is going to be about 0.956 millimeters. Okay. And longitudinal strain, that's going to be epsilon sub L equals sigma sub L minus nu sigma sub h over E. And our volumetric strain, that's going to be epsilon sub V equals 2 epsilon sub h plus epsilon sub L, and that's going to yield epsilon sub V is about 1.78 times 10 to the negative 3rd. And that's all for number 4. Let's move along to number 5. For number 5, we have a solid steel shaft transmits power from a motor to a gearbox. The shaft length is 2.5 meters and diameter 50 millimeters. Shaft rotates at 360 RPM while transmitting 85 kW. Okay, so we're given this. The G is 80 GPa. Determine A, the transmitted torque, B, the maximum shear stress in the shaft, C, the angle of twist between the ends, and D, the maximum stored torsional strain energy. So this is a torsion of circular shafts type problem. So we take our power relation, P equals T omega. Omega now substituting, this is going to be 2 pi times 360 over 60 using what we know about omega. It's 37.70 radians per second. To get T now, it's just going to be that 85,000 divided by what we have for omega, 37.70. So T is about 2.25 K and M. All right, so our polar moment is going to be J equals pi d to the fourth over 32. Our maximum shear stress, our tau sub max, that's going to be T sub C over J. So just substituting our values here, our tau sub max is 91.9 MPa. Okay, so from here, moving along here, angle of twist. Angle of twist, that's going to be phi equals TL over JG. Phi is about 0.115 radians, which is about 6.58 degrees. Okay, so the strain energy is going to be U equals T squared L over 2JG, and that U is going to be about 129 joules. So that takes care of number 5. Let's move to number 6. Okay, number 6. Okay, so number 6, a composite shaft consists of an inner steel core of diameter 40 millimeters and an outer brass tube with outer diameter 70 millimeters. The two materials are perfectly bonded and subjected to a total torque of 6 Kn/m. Material properties are steel, G sub S, 80 GPa, brass, G sub B, 40 GPa. Okay, these three things, we want to determine the torque carried by each material, the maximum shear stress in steel, the maximum shear stress in brass. So, composite shaft problem. What we could say is the same angle of twist means the torque splits in proportion to GJ. So what we could say this is T sub S equals T times this quantity G sub S, J sub S over G sub S, J sub S plus G sub B, J sub B. And T sub B equals T times G sub B, J sub B over G sub S, J sub S plus G sub B, J sub B. So when we substitute all our values, our results are going to be T sub S is about 1.16 Kn/m, T sub B is about 4.84 Kn/m. The steel shear stress, tau sub S, is about 92.0 MPa, and the brass shear stress, tau sub B, is about 80.5 MPa when we substitute. Okay, that's number 6. Moving along to 7. Okay, so number 7, we have a simply supported beam of span 6 meters carries a uniformly distributed load of 8 Kn/m per m over the entire span card, and a concentrated load 20 Kn located 2m from the left support. Okay, so determine these 4 things: the support reaction, the shear force diagram, the bending moment diagram, location and magnitude of the maximum bending moment. Okay, so some of this I omitted for number 7. I'm just going to do some of it, and you could do the rest if you want. Beam shear and bending moment, total distributed load with W equals 8 times 6, 48 Kn. Moment about the left support, R sub B times 6, that's going to be 48 times 3 plus 20 times 2. That gives you 184. Isolating R sub B, 184 over 6 is about 30.67 Kn. Okay, so that's for R sub B, and R sub A is 37.33 Kn. Okay, so we have R sub A, R sub B. Now for these intervals, for 0 is less than x is less than 2, V equals 37.33 minus 8x, M is 37.33x minus 4x squared. And for the interval from 2 is less than x is less than 6, V is 37.33 minus 8x minus 20, and then V is 17.33 minus 8x. So our m of x here is 37.33x minus 4x squared minus 20 times the quantity x minus 2. So our maximum moment occurs where v equals 0 after the point load. So 17.33 minus 8x is 0. So x is about 2.17 meters. So our m sub max is about 48.8 kNm. Okay. So I omitted some stuff there, but that's the basis of number 7. Moving along to number 8. Let's see. Wooden. Number 8. A wooden beam with rectangular cross-section, width 120 millimeters, height 300 millimeters, is subjected to a vertical shear force V equals 45 kN and a bending moment M equals 18 kNm. Determine these 4 things: the maximum bending stress, the bending stress 75 mm above neutral axis, the maximum transverse shear axis, the shear stress 50 millimeter from the neutral axis. Okay, so this is a bending stress and shear stress distribution problem. We're going to need the moment of inertia. In this case, moment of inertia is I equals BH cubed over 12. At 75 mm above neutral axis, sigma is m sub y over I. So sigma is about 5.0 MPa. The maximum rectangular beam shear stress, tau sub max, is 3V over 2A. So when we calculate that, that's tau sub max is about 1.88 MPa. And at this specific portion, this specific amount, y equals 50 millimeters, t equals 3V over 2A. We're going to use this formula. Tau equals 3V over 2A times the quantity 1 minus 4y squared over h squared. And here our tau is about 1.67 MPa. And over here, forgot to mention this. I skipped over some stuff. The maximum bending stress, sigma sub max, it's MC over I. That sigma sub max is about 10.0 MPa when you do the computation. So I went over this. This is basically a shell of step-by-step of how you would go and arrive at the conclusions for your values that were computed. Again, intermediary steps, a lot of them are omitted, but this is so you have a reference. Number 9. Okay, so what we have for number 9, cantilever beam of length L carries a uniformly distributed load over the entire span and concentrated load at the free end. The beam has constant flexural rigidity, EI. Using direct integration of the electric curve equation, determine A, the slope at the free end, B, the vertical deflection at the free end, C, the location of maximum curvature. So this is a beam deflection by integration. Okay, so again, for this, I omitted a lot of the computation. So just getting to the ending here, for a cantilever with end load P and uniform load here, free end slope is this. It's just going to be theta sub L equals PL squared over 2EI plus this quantity here. So that's for your free end slope. And right here for your free end deflection. Okay, this is, I apologize for my very poorly drawn delta. This is delta sub L equals this portion here. And one final note here, the location of maximum curvature, that's just going to occur at x equals 0. Because that's where the bending moment is largest, which is at the fixed end. Okay, so I went over that pretty fast. Again, you could try that. This is more of a problem you try. Okay, and that's moving along to number 10. Let's see. Okay, 10. A steel column with pinned ends has length 3.2 meters and a square cross section 80 millimeters by 80 millimeters. The material properties are E equals 200 GPa. Yield stress 320 MPa. Determine these 4 things: the Euler critical bulking load, the corresponding critical stress, whether Euler buckling theory is appropriate for this column, and for D, the factor of safety against buckling if the applied load is 180 kN. So column buckling for pinned ends. This is going to equal pi squared EI over L squared. For the cross section, you're going to get I is a to the fourth over 12, so that's going to be 0.08 to the fourth over 12. So that's going to give us, for that cross section, 658 kN. Critical stress, that's sigma sub CR is PCR over A. So we're going to wind up with this sigma sub CR is 102.8 MPa. And since our sigma CR is less than sigma Y, Euler buckling is reasonable for this situation. And our factor of safety, Fs, okay, P sub CR over P applied, Fs equals 658 over 180, so the Fs is about 3.66. Okay, so that takes care of that one. And now number 11. Okay, number 11, a circular rod of diameter 45 millimeters is subjected simultaneously to axial tensile force P equals 110 kN, torque T equals 2.8 kNm, and bending moment M equals 5.5 kNm. Determine at the outer surface these 5 things: the normal stress due to axial load, the bending stress, the torsional shear stress, the principal stresses, and the maximum shear stress. Okay, so combined loading problem, area of this is going to be pi d to the fourth over 4. Axial stress is going to be sigma sub A is P over A. So our sigma sub A is going to be about 69.2 MPa. Bending stress, sigma sub B, that's MC over I. So sigma sub B is going to be 614.8 MPa. Just substituting the values and computing. Total outer surface normal stress on tensile side, that's going to be sigma is the sum of sigma sub A plus sigma sub B, and that's going to be about 684.0 MPa for sigma. Our torsional shear stress, that's going to be tau is about T sub C over J, which is going to lead to 156.5 MPa approximately. Our principal stresses here are sigma sub 1 comma 2 equals sigma over 2 plus or minus the square root of that's sigma over 2 squared plus tau squared. So substituting values for sigma sub 1, we get 718.1 MPa. And for sigma sub 2, we get negative 34.1 MPa. So the maximum shear stress, that's tau sub max, is about 376.1 MPa. Okay, so moving along now to our last one, number 12. So for this one, let's see here. Okay, so we have a 45 degree strain rosette records the following strains. So we have E, epsilon sub A is 420 times 10 to the negative 6. Epsilon sub B is 110 times 10 to the negative 6. And epsilon sub C is negative 180 times 10 to the negative 6. So for material with E equals 210 GPa and nu equals 0.29, determine the 4 following things: the in-plane strain components, epsilon sub x, epsilon sub y, gamma sub xy, the principal strains, the principal stresses, and the maximum in-plane shear stress. Okay, so this is a strain rosette and generalized Hooke's law problem. So assume the 45 degree rosette gauges are arranged as A equals 0, B equals 45, C is 90. Okay, given here, epsilon sub A is 420 times 10 to the negative 6, epsilon sub B 110 times 10 to the negative 6, epsilon sub C is negative 1.80 times 10 to the negative 6. For part A here in the plane strain components, for a 0, 45, 90 rosette, E sub x is EA, E sub A, E sub y is E sub C, and then gamma sub xy, that's going to be 2 epsilon sub b minus epsilon sub a minus epsilon sub c. So epsilon sub x is 420 times 10 to the negative 6. Epsilon sub y is negative 180 times 10 to the negative 6. And our gamma sub xy, that's 2 times the quantity 110 times 10 to the negative 6 minus 420 times 10 to the negative 6 minus a negative 180, that quantity times to the negative 6. So our gamma sub xy is going to be negative 20 times 10 to the negative 6. That's one way of writing it. So we have our quantities here for E, epsilon sub x, 420 times 10 to the negative 6, epsilon sub y, negative 180 times 10 to the negative 6, and gamma sub xy, negative 20 times 10 to the negative 6. Okay. Now for part B, principal strains. The principal strains are, we'll use this, epsilon sub 1 comma 2. That's going to be epsilon x plus epsilon y over 2 plus or minus this. Formula square root of this epsilon sub x minus epsilon sub y over 2 squared plus gamma sub xy over 2 squared. Okay. The average strain is going to be E sub epsilon sub x plus epsilon sub y over 2. So it's 420 minus 180 over 2 times 10 to the negative 6. You get 120 minus 10 to the negative 6 for that. Okay. And then we're going to be substituting values here. Okay, so we're going to take the square root of this, 420 minus 180 over 2 squared plus negative 20 over 2 squared times 10 to the negative 6. Okay, and we're going to get 300 squared plus 10 squared times 10 to the negative 6. So this is 300.17 times 10 to the negative 6, about that. So therefore here for E sub 1, 120 times 10 to the negative 6 plus 300.17 times 10 to the negative 6. That's going to yield about 420.17 times 10 to the negative 6. And for E sub 2, 120 times 10 to the negative 6 minus 300.17 times 10 to the negative 6. So that's going to come out to about negative 180.17 times 10 to the negative 6. So that's for letter B. Letter C, we want the principal stresses. Letter D, the maximum in plane shear stress. That's on the next page. Okay, so here, principal stresses here. For plane stress, we have sigma sub x equals E over 1 minus nu squared times this quantity, epsilon sub x plus nu epsilon sub y. And then epsilon sub y equals E over 1 minus nu squared times the quantity given there as E sub y, as epsilon sub y plus nu epsilon sub x. And our tau sub xy, that's going to be G gamma sub xy. And this is where G is E over 2 times 1 plus nu, that quantity. G equals 210 GPa over 2 times 1.29. So our G is about 81.4 GPa. So our sigma sub x is 210 GPa over 1 minus 0.29 squared times this whole quantity here, that 4.20 times 10 to the negative 6 plus 0.29 times the quantity negative 180 times 10 to the negative 6. And then that's where we get sigma sub x is about 84.33 MPa. Sigma sub y, 210 GPa over 1 minus 0.29 squared. And now that's going to be multiplied by this. Negative 180 times 10 to the negative 6 plus 0.29 times 420 times 10 to the negative 6. So our sigma sub y yields about negative 13.34 MPa. Our tau sub xy, that's 81.4 GPa times the quantity 20 times 10 to the negative 6. So our tau sub xy is about negative 1.63 MPa. So now using the principal stress formula, our sigma sub 1 comma 2, that's sigma sub x plus sigma sub y over 2 plus or minus the square root of quantity in the numerator, sigma sub x minus sigma sub y over 2, that quantity squared, plus tau sub xy squared. And our radius, when we substitute all those values in, so that's 84.33 minus a negative 13.34 over 2 squared plus negative 1.63 squared here. And that's going to be about 48.86 MPa. So we wind up getting our values when we compute this as sigma sub 1 is about 84.36 MPa. Sigma sub 2 is negative 13.37 MPa. Okay, and moving along, part D, maximum in-plane shear stress, tau sub max equals square root of quantity sigma sub x minus sigma sub y over 2 squared plus tau sub xy squared. So our tau sub max is about 48.86 MPa. And just adding on to this, a note here at the bottom that's important. The principal strain values in this problem are extremely close to the original strain components because the shear strain is very small. Okay, so that's all. This is just an overview. Hopefully this gives you some extra practice if you're getting ready for an exam of this nature. My apologies if I miscommunicated anything, and I did go a bit fast. Again, there were a lot of steps that were not shown, but these could be used as extra practice problems. So thank you very much, and have a great day.